Hello and welcome back. So today we're going to continue with a lesson on set theory. So this is a whole new topic. So I hope everyone is caught up to where we are at in the course so far. But here we're going to start anew. We're going to start with the topic on set theory. If you've never heard of this topic, it's okay. We're going to start right from the bottom and kind of build our way up. Now, set theory is a pretty big topic. We're going to spend a couple of videos at least on this, a couple of weeks of videos on this at least. So we're going to start off by giving some basic definition. So what is set theory? It turns out that you've probably, if you've taken an intro course in math, you've probably seen some notations in set theory, but we're gonna formalize it here. We're going to talk about some set notations and set operations and laws and what those are. You're going to see a very a similar analogy to the laws that we've talked about before with the laws of logic. So keep stay tuned for that. We're also going to talk about counting as pertains to set theory. We talk a little bit about what Venn diagrams are, inclusion, exclusion, and these are all counting concepts that are in set theory. We're going to finish off this section by talking about some applications in set theory, including probability. Again, probability is probably something you've seen before in math. We're going to take a look at what probability actually means pertaining to set theory. And then we're going to finish off by talking about conditional probability, something you probably have not seen before, and expected values. Again, something that you probably have not seen before, but are good applications and are good setups for things that you're going to see down the line, especially if you are going to take something in stats or computer science or something like that. So let's start off with some definitions. What is a set? So whenever we talk about a set in this course, we're talking about a theoretical structure which is used to group objects together. Okay, so theoretical structure or a box that is used to group objects together. So what does that really mean? A set is really a description of a bunch of objects. So when we talk about a set, we're saying, we're giving really a description of a group of objects. And these objects are called elements or members of the set. So for example, I can give you an example of a set like A is equal to all SFU students. Okay, so all SFU students. And B could be all Macom students or discrete math students, let's say. Okay, so we can assign these sets as variables. And typically the variables that we assign these sets are capital letters. You'll see like examples as A, B, C, or X, or Y, or Z. These are typical names that we would give as a variable to a set. Now, this is very similar to what we've talked about in propositional logic. So when we had a logical statement, we would label it as P or Q or something like that. So this is no different, except we are using capital letters. Now, there are other things that we're going to explore later on in this topic, which is if I have a set A and a set B, there are certain operations that I can apply on there. So for example, you might imagine that in this case, set A and set B, the elements, the objects that are inside the set are students. Right? In fact, they are, in the first case, SFU students, and B, in the case of B, they're discrete mathematics students. So what we can do is take a common object of A and B. So if we apply an operation like common object, what this means is I want the elements that are common to A and B. And I hope you can see we have another set. We have a third set, which is all discrete math students who attend SFU, right? So SFU, discrete math students. And this is, in contrast to other universities, discrete mathematics students. So you can see that we can actually do a few things with these sets, but we're going to leave that for a later discussion. But for now, I just want to talk about different ways that we can express a set. So for example, I can say that I have a set A, which is the set of positive even numbers that are less than 10. Less than 10. Okay, so the set of positive even numbers that are less than 10. So we can then say that A can be expressed as what we call an open form. So the first way of describing a set is just simply writing it out in English, and that is acceptable because we know that we're dealing with a theoretical structure. The second way is we can actually put it into an open form. So open form means I use these squiggly brackets. Now, anytime you see squiggly brackets, we are really talking about a set. So all the properties that go with a set. Now, I'm going to explain what a property is about a set a little bit later on. But for now, let me just say that in the open form, we have these squiggly brackets. And I'm going to list out all of the numbers that are inside. So we have 2, 4, 6, and 8. Okay, so we have these numbers that are the elements or the objects that are inside of a set. Now, you might look at this and say, okay, this is very straightforward. We can see all the elements that are inside. But what if we had more? What if I wanted to have the set of positive integers or positive numbers? I should probably say integers here, just to indicate that they're whole numbers that are less than 10. Okay. So do I have to write out everything from 2 all the way up to 90? Sorry, the set of positive even numbers that are less than 100. What if I said I wanted those? Do we have to write out all of the elements from 2 all the way up to 98? And no, we don't actually need to do that because there's a third way to express a set, and that is with a closed form. So this is what's called an open form. Okay, there's another one that is a closed form, and a closed form is a little bit more difficult, but it's actually something that you've probably seen in mathematics textbooks or other places. We give a form for this number. So since this is a positive number, or sorry, since this is an even number, it is always in the form of 2k. I'm going to say that k is going to be between 0 and 5. Okay, and k is an integer. So I've given you all of the information that you're going to need in order to compute all of the elements that are inside this set A. So here, if we wanted to expand this, if we want a set of positive even integers that are less than 100, then I can just change my k's to change the range of the numbers that I want to represent. And once again, this is called a closed form, or it's called a set builder form. So set builder meaning that you have all the information to build the set mathematically. So basically 3 ways that we can represent a set, and all 3 of these ways are valid. So anytime I say, give me a set that is this, this, and this, you can choose any of the 3 ways. All right, now in addition to this, we have other notations to indicate whether an element is found inside of a set. So for example, I can say in our case that 2 is in the set A. So 2 is found in the set A. It is an element that is found in set A because it's right here, right? This is one of the elements. So we call this a 2 is an element of, we read this as 2 is an element of A. Similarly, we can say that 3 is not an element of A. So we use this kind of E symbol with the slash, and we can say 3 is not an element of A. Now, please be careful here because as we expand on our definitions, this definition is going to become a little bit more fuzzy. But anytime you see this E, this kind of epsilon, it means that the element on the left-hand side, the element is found in the set, in this case, A. Okay, so this element is found in A. So just please keep that in mind because as we get to larger and larger sets, this is actually going to get a little bit more confusing, and I'll keep reminding you of this. Now, lastly, the thing I want to the last thing I want to point out here is that we have a special set which is empty. So I can define a set which is empty, which has no elements in there, and we use this squiggly bracket with nothing inside to indicate an empty set, or we can simply use a 0 with a slash. So this 0 with a slash is defined as empty set. Okay, so the way that we can think about it later on when we do proofs is probably something like this, but typically we will use just this empty set symbol in order to represent an empty set. Now, There are some important sets that we're going to use throughout the course. So I just want to very quickly share with you what those represent. So the set Z, whenever we use Z, that is a set that is reserved for the set of integers. So 0, 1, -1, 2, -2, and so on. So the set of whole numbers is Z. N is the set of non-negative integers. So non-negative integers are ones that start with 0. So 0, 1, 2, 3, and so on. Okay, so set of non-negative, so anything that's not negative belongs in this set. We also have the set of positive integers. So positive integers start at 1. Okay, so this is Z plus, and this is N. Now you might be asking, what's the big deal about the difference between non-negative integers and a set of positive numbers or positive integers? Well, it turns out that it's actually quite different. There's a big difference between the two, and we're going to get into some of that. So we're going to get into what the differences are between non-negative and positive integers, especially once we get into proofs a little bit later on. But just remember, there is a difference between the two. Okay, so we have the set of non-negatives. We also have the set of positives. Okay, so those are integers, those are whole numbers. And primarily, we're going to do a lot of work with those three throughout the course. But you also need to know that we also have a set of rational numbers. So the definition of a rational number is we can write this number in the form of x over y, where x and y are both integers. Okay, so x and y are both integers and y cannot be 0. So a rational number is a number in which we can write it in the form of x divided by y, where y is not an integer and both x and y are integers. Sorry, y is not 0 and both x and y are integers. Okay, so we also have the set of positive rational numbers and the set of non-zero rational numbers. So try to remember that. We also have a set of real numbers. A set of real numbers are just any numbers that you can think of. We have the positive real numbers and we have the non-zero real numbers as well. So those are represented by r plus and r star respectively. So if you want to know what the difference between rational numbers and real numbers are, is that real numbers is a larger set than rational numbers, even though they're both infinite. Okay, we're talking about infinite sets in 1 second. They're both infinite. They both have infinite number of values in there, but the set of real numbers is actually bigger. So one example that I can give you is the number root 2 is a real number. Okay, so if you figure out what root 2 is, it actually goes on forever. Okay, but root 2 is not a rational number. So it's not in the set of Q. So there's no way that we can write root 2 in the form integer over integer. Okay, so there's no way that we can write that. So you can see here that R is actually a bigger set than positive rational numbers. And by the way, every rational number is a real number. Right? Every rational number is a real number, but not necessarily the other way around. Okay, and we'll get to some of that a little bit later. Now, the last one here is the set C. C is probably not something that we're going to discuss in this course, but whenever you see the set C being used in other textbooks, usually they're referring to something like set of complex numbers. So complex numbers being a plus bi, where I squared is equal to -1. So these are imaginary numbers. We also have the set of non-zero complex numbers that are represented by C star. But for the most part, I think Z, Q, and R are the sets that we're going to use the most in this course. So please keep note of those and know what they mean. Okay, a few more definitions for set theory, and that is given a set A, the cardinality or the size of A is the number of elements in A and is denoted by these two straight lines and A. Now, I'm going to add another word here, the number of different elements. Now, in a second, you're going to see why I add this keyword in here. But in short, the cardinality of a set or the size of a set is that we just count the unique elements that are in that set. Right? So for example, if we go back and take a look at our example here from from 5-2, our A was 2, 4, 6, and 8. So if we take the same example, 2, 4, 6, and 8, we can say that the size of A is equal to 4. There are 4 unique elements in this set. So, well, let's just take a look at some sets that we saw before. So, for example, we can say that the set Z, right, the set of integers is infinite. So the cardinality or the size of Z is infinity. Similarly, we can say Z plus is also infinity. We can say that the empty set. So what is the size of the empty set? Well, by definition, there's no objects inside. This is a 0. Now, we should make a distinction between what we call finite and infinite sets. Okay, so there are finite sets and there are infinite sets. In short, if the number is countable, if the size is countable, then we would call this a finite set. If the size is not countable, we call it an infinite or infinite set. So here, this A is finite. The empty set is also finite because it is represented by a number. And in these two cases, these are infinite sets. Now, as I said before, even though Z and Z plus are both infinite sets, right? They have infinite objects inside. We can still make a claim that the size of Z is bigger than the size of Z plus. Now, this is a discussion that I'm going to leave for a different course, but just understand that even if we had infinite sets, there could be a relationship between these sets in that one size could be theoretically bigger than another. Okay, so let's get on to the next definition here. We have a next definition where we want to define what's called a subset and a proper subset. So for example, if I give you two sets and we'll call this example 5-3, we'll label this one down here 5-4. If I give you two sets, A is the set 1, 2, 3, and B is the set 1, 2, 3, 4. And let's actually add a third set. We'll call it C, which is also 1, 2, 3. Okay. All right. So when we say that there's a set is a subset of another set, we're basically saying that every element from the first set is also found in the second set. So for example, if we write this is read as A is a subset of B. That means every element in A is also in B. Okay, every element in A is also in B. That is what we mean by the subset. So for example, in our case, can we say that A is a subset of B? Yes, we can, because every element in A is also found in B. All right, can we say that B is a subset of A? Can we say that every element in B is also found in A? No, we can't, because the number 4 is not found in A. We have to make sure that every single element in B is also one that is found in A. So here we cannot say that B is a subset of A. Can we say that A is a subset of C? Is it true that every element in A is also found in C? The answer here is yes. Okay, because you analyze A has the numbers 1, the number 2, and the number 3, and all 3 of those elements are found in C. So that's what a subset means. Now, in a second, I'm officially going to write down the definition for a subset, but just know that in English, that's what that means. Okay, next, I want to add a little bit more to this, which is called a proper subset. So the proper subset is denoted as this. So you notice that the only difference between a subset and a proper subset is it doesn't have this line underneath. So what's so special about this line underneath? Well, in short, the proper subset has an extra constraint to it. So if A is a proper subset of B, if A is a proper subset of B, that means every element in A is also in B, and there's an extra element in B that is not found in A. Okay, so the first part of this definition is exactly the same as subset. Every element in A is also in B, and there's an extra element that's in B that is not found in A. Okay, so let's analyze. Can I say in this case that A is a proper subset of B? Yes, I can, because every element in A is found in B. And there's an extra element, which is 4, that is found in B that is not found in A. So yes, it is a proper subset. Can I say B is a proper subset of A? And here the answer is no, I cannot. Okay, because it failed the first test. It's not true that every element in B is also in A. So B was not a subset of A. I can't say anything about proper subset. Okay, so as soon as you find that it's not a subset, right away, we can't say anything about proper subset. Okay, is A a proper subset of C? Once again, the answer is no. So even though A is a subset of C, every element in A is also in C, we can't find an extra element in C that is not in A. Okay, so I can't find that extra element. So in fact, they are equal. So what does that tell you in English? The relationship between subset and proper subset. Well, the relationship is actually very similar to less than, strictly less than, and strictly less than or equal to. I shouldn't have said strictly there. So less than or equal to. So for example, if I say a number A is less than or equal to B, they could be equal, right? But if I said A is less than B, then it must be strictly less than. Okay, so I hope you see the relationship here between subset and proper subset. Okay, so with that said, let's see if we can give a full definition of subset and proper subset. All right, so first, let's give a definition. So we'll call this definition 5-1 because I actually want to write out this definition. The definition of a subset goes like this. A is a subset of B if and only if. Now remember what we said about this if and only if, right? This is actually a logically equal, which is a definition, right? But this definition means that it can go both ways, right? And we are defining upon an if and only if. Okay, so A is a subset of B if and only if. For all elements, if that element is in A, then that element is in B. So this is our official definition of a subset. If the element is in A, then the element has to be in B. Okay, that is the definition of the subset. Now you might be asking, what if I have an element that's not in A? Does it have to be in B? No, it doesn't. Right? So the only direction that we care about here is that if we have an element in A, that element must also be in B. So please, again, if this doesn't make sense to you, you can pause the video here. Just make sure that you understand this concept. But this idea, this logic is going to come back, and we're going to use it over and over. Now, the first thing I'm going to do here is I'm going to highlight this definition because this is one of the definitions that we will be using whenever we talk about subsets. All right, now I say this is one of the definitions because there's actually another way that we can write this, or another way to perceive subset, another way to define subset. So the way that we can do this is apply the implication reduction to this statement. So we can have something like for all x, I'm going to take the not out of the bracket here. So you can imagine that this is our P, this is our Q, right? So if we have P implies Q, this is the same as not P or Q. And then I'm going to pluck a negation out of this bracket. Okay, so just bear with me here. I'm just going to write this down. We have P and not Q. Okay, so if we take a negation out of this bracket, we're going to end up with not P and not Q. All right, so I hope everyone sees that these three expressions are actually equal to each other. So if I have P implies Q, it is the same as saying not P and not Q. Okay, again, if you're unfamiliar with this, please go back and review the logic laws that we talked about before. Okay, now, of course, we can actually go one step further, and I can take this negation even further outside the quantifier, and this can become, the negation of exist x. So please make sure that you understand why those two are equal to each other. Now, this second statement that I wrote down is actually not that useful in the readability. However, if I decide to find out what is not a subset, so what is the definition of not being a subset? Well, I can negate both sides. So I negated this side. So A is not a subset of B. I'm going to negate the other side, which means I just get rid of this negation. So I'm left with there exists X and then X in A and X not in B. So how is it that I can determine that something is not a subset, A is not a subset of B? Well, if there is an element that is in A and not in B, that's enough to say that A is not a subset of B. Okay, so again, if I can find even one element, there exists an element X that is in A and is not in B, right away I can say A is not an element of B. So let's go back. Here, I said B was not a subset of A because there's an element in A and is not in B. So there's an element in this set and is not in this set, which is the number 4. Okay, so there is an element in here, which is not in here. Okay, I hope everyone got that. That is why we can say is not a subset. Oh, by the way, the symbol for it is not a subset is the subset symbol with a slash across. So that's indicating not a subset. All right, let's give one more definition here because we have a little bit of room here. So I'm going to take A is a proper subset of B. So what is the definition there? But before we write out the definition, I'm actually going to highlight this part here because this is the other definition that I'm going to need for later on if I want to do a proof. This is the official definition of not subset. All right, but what about proper subset? So I'm going to take number 1. Okay, number 1 is part of the definition. Remember I said if A is a proper subset of B, it must qualify to be a subset first, right? So 1 must be true. Okay, so everything in A is also in B. And okay, I'm going to take that statement. And the second part of this definition is there must be an object that is in B and it is not in A. Okay. So the first definition is everything in A has to be in B. And the second part is there has to be an object in B that is not found in A as well. Okay, so there's 2 parts to that definition. So again, I'm going to highlight this because later on we're going to need this as a definition as well. So, oops, I wanted a highlighter. So I'm just going to highlight this definition, and later on we're going to come back and we're going to use this in a proof and whenever we need it for other things as well. Okay, one final definition, and then I think we can move on to something a little bit more practical, which is example 5-5 here. We haven't really defined equality between 2 sets. Okay, so given sets A and B, A is said to equal B and denoted as the equal sign. So this equal sign we're going to use for sets as well, if and only if. So here's the definition. A and B contain the same elements. So A and B contain the same elements. That's all is required for A and B to be equal to each other. So as an example, we can say that 1, 2, 3 is equal to 3, 2, 1. Okay, so according to the definition, these 2 sets contain the same elements. Yes, they do. So this is true. This is a true statement. So 1, 2, 3 is equal to 3, 2, 1. So what you can gather from this is that one of the characteristics of a set is that order doesn't matter. Okay, so if I give you the statement, if I give you the set 1, 2, 3, and I give you the set 3, 2, 1, the order doesn't matter. They are the same set. So you can start to think when we start counting, when we incorporate counting into set theory, what type of counting do you think it's going to be? Right, so the one without order. Another example, if I gave you 1, 2, 3, the set 1, 2, 3, is it equal to the set 3, 3, 3, 2, 1, 1? Are those equal? Now, I want you to think back. When I talked about size, when I talked about cardinality, what did I say about the number of elements in A? Well, we added a word there that said different. It's the unique elements in A. So you might be saying, well, how come there's three threes and there's two ones? Well, where did those things come from? I'll answer that question in 1 second. But right now, I just want to answer, are these two sets equal? The answer is yes, because they in fact contain the same elements. Both sets contain the same elements. And in fact, the size of both sets are equal to 3. Okay, because ultimately, when we're counting the size, when we're counting the cardinality, the only thing we care about is the unique elements, right? How many different elements are there in the set A? All right, now back to the question. How is it that we can have several elements that are the same in the set? Well, the short answer is we can't really. We can't really have this. But when we have a duplicate 3, the application here, or the idea here, is that this is an application in databases. So for example, if you have a database and you have a bunch of objects in your database, sometimes these objects are duplicated and they are indicated by an identifier. Okay, so the idea in a database, now, if you've never heard of a database, if you don't know what that is, it's just a computer that keeps track of a bunch of data. So each piece of data is usually uniquely defined. So I give it an ID. I give each piece of data an ID. And these IDs can never really be duplicated, right? So theoretically, they cannot be duplicated. But sometimes in the form of calculations, in when we are calculating certain things in a database, certain objects get duplicated. And we should only view those objects as being one. Okay, so whether you got that application or not, that is why there are sometimes in a set that you might see duplicated objects. But at least in this course, understand them as only one object. Count them as only one object. Okay, so that is equality. So equality means that the elements in A and the elements are in B are the same. Okay, so the next thing that I want to point your attention to is a Venn diagram. So a Venn diagram shows the relationship of a set to other sets as well as the universe. So Venn diagrams, again, probably are something that you've seen before in math courses or something like that. I'll give you a very simple example of a Venn diagram. So in this case, we have the relationship A is a subset of B. All right. So the first thing we have is kind of like a universe. Okay. So this is U. We're going to label this as U. This is like our universe. These are all the objects that you can think of. Okay. They can be any objects. Okay. For example, if A takes up this space, okay, so every object in A is in that circle, then how do we draw the relationship that A is a subset of B? Well, it means every object in A is also in B, right? So that means that B must look something like this. Okay, now notice that this just gives you a relationship. The only thing that this defines is a relationship between set A and set B. All this is telling you is that everything in A is also in B. That's all it's telling you. It doesn't tell you how big A is, how big B is, how big U is. It doesn't tell you any of those things. A could be empty, right? B could be empty. We don't know. So the only thing that Venn diagrams typically tell you is relationships between sets. Now, one good thing about a Venn diagram is we can also incorporate this idea into a proof as well. So as an example, if you take a look at example 5-7 here, we have a statement that given sets A and B, A equals B. Now, again, remember what A equals B means. A and B contain the same elements, right? So A and B contain the same elements. They are equal if and only if A is a subset of B and B is a subset of A. All right, so let's see if we can kind of work out this proof. Now, I'm going to start with, let's see here. I'm going to start with the forward direction. Okay, so if A is equal to B, so if A is equal to B, is it true that A is a subset of B and B is a subset of A? Can we say that automatically? I think so, right? Because automatically, if they contain the same elements, every element in A is also in B. every element in B is also in A. So this is automatically true. Okay, even if we just use the definition that we had from the previous slide, we just use this definition, we can say both of those have to be true if A is equal to B. The thing that's not as clear is, does the other direction work as well? Because this is an if and only if. I want to show if A is a subset of B and B is a subset of A, can we conclude that A equals B? Okay, let's use a Venn diagram to help us. So I have this here. I have set A and I have set B. Okay, so this is A is a subset of B. Okay, so A is a subset of B. And I'm going to draw a diagram that says B is a subset of A. So we have B is a subset of A. Okay. So now we are talking about the both of these cases being true, both of these Venn diagrams being true. Okay. So the first thing I want to point your attention to is this area right here. So if I just highlight this area, okay, can we describe what this area is? Well, it must be all those elements that are in A, but not in B. Okay, all of those elements that are in A, but is not in B. All right, so my claim here, or at least I want to show that this area must be empty. Okay, the elements that are in A, but not in B, must be empty. Now, I hope you can see that if I'm able to prove this, if I'm able to prove that if every element, the elements in A that are not in B is empty, then they must be equal. The A and B here in this diagram must be equal. Okay, so just take a second to convince yourself that that is a true statement. But how do we prove this? How do we prove that elements that are in A and not in B is empty? Well, let's take an opposite approach to this. So that means I want to do a kind of a mini proof by contradiction. Okay, so the thing I want to prove is that the elements in A, so there is no element in A and not in B. Okay, this is what I want to prove. Okay, so in this mini proof by contradiction is I want to assume the opposite. Remember proof by contradiction, the first thing I'm going to do is assume this statement is false. Okay, how do I assume this statement is false? I'm going to assume that there is an element that is in A and is not in B. Okay, I'm going to assume there is an element in A and not in B. And my goal here is to show that this cannot happen. This is going to derive a contradiction. Okay, now luckily, we've seen this before. If you go back one slide and you take a look at this definition, if there is an element in A and not in B, okay, what can we say? I'm sorry, this one right here. If we can say, if there is an element in A and not in B, what can we say? We can say right away that A is not a subset of B. So just from this, we can say A is not a subset of B. But where's the contradiction? Well, the contradiction is we assumed that A was a subset of B, right? That we already assumed this. So we have the fact that A is a subset of B and A is not a subset of B. This is a false. So therefore, there cannot be any elements in this area. Okay, so we've just proved that there cannot be any elements in A and not in B. So therefore, as a kind of a finish to the bigger proof, we can say that A must equal B. So from the fact that A is a subset of B, B is a subset of A, we can conclude A equals B. Okay. So I hope this is a good introduction to what we're going to do for set theory. The set theory, again, it requires a lot of knowledge of these definitions. So what I would recommend right now is to go back and just review these definitions that we just talked about, especially the element. What does the element mean? What does a subset mean? What does proper subset mean? And just know those definitions because in the next part, you're going to need those definitions. Okay, so I'm going to stop the video here. I'm going to see you again in the next video where we pick up from this concept.